Welcome to our course on machine safety. This course aims to provide an overview of the key principles and standards governing machine safety. We'll focus on important aspects of ISO 12100 and other relevant standards to help you understand how to design and operate machines safely. It's important to mention that this course is not an alternative to the standards. This is not a comprehensive list, and many detailed requirements are not addressed here. Our goal is to highlight the most important items related to machine safety so that you can understand the foundational concepts. For a complete understanding, always refer to the full text of the relevant standards. Let's begin. This course is divided into 3 parts, each addressing crucial aspects of machine safety. Part 1 covers a short introduction, selected terminology, key concepts, and selected definitions. This section also describes the approach to risk assessment and risk reduction briefly, followed by some examples of machine hazards. In Part 2, we focus on risk assessment in detail. Finally, Part 3 presents the most important points related to risk reduction. We conclude the course with a summary. Let's begin this journey by reviewing the key components of machine safety, primarily based on ISO 12100. Welcome to Part 1. In this section, we'll start with the introduction, setting the stage for our exploration. We'll then present a selected group of terminology, key concepts, and definitions that are usually employed when dealing with machine safety. The approach to risk assessment and risk reduction is introduced briefly. At the end of this section, we outline some examples of machine hazards. Join us as we start this course. In the introduction, we uncover the importance of machine safety and the essential principles of ISO 12100. Machine safety is a critical aspect of industrial operations. It involves implementing measures to protect operators, maintenance personnel, and the environment from machinery-related hazards. One of the fundamental standards in this field is ISO 12100, which provides general principles for risk assessment and risk reduction in machine design. This standard emphasizes the machine's ability to perform its intended functions throughout its life cycle while ensuring appropriate risk reduction and promoting the importance of documentation, information for use, and training. We'll discuss the key elements of this standard and how it helps ensure safety at every stage of machine design. All standards are categorized into 3 types, namely Type A standards, Type B standards, and Type C standards. ISO 12100 belongs to the Type A standards category, serving as the foundation for a broader set of standards. These include Type B standards, which address generic safety aspects applicable to various machinery, and Type C standards, which provide detailed safety requirements for a specific machine or group of machines. A crucial point to note, in cases where a Type C standard differs from ISO 12100 or a Type B standard, the Type C standard takes precedence. This highlights its importance in specific contexts. This table shows a selection of machine safety standards categorized by different types. As mentioned earlier, ISO 12100 is a Type A standard. We will also discuss IEC 62061 and ISO 13577 Part 2 standards later in this course, as they represent Type B and Type C standards, respectively. Now, let's briefly review some selected terminology we'll encounter later. These terms are essential for understanding machine safety standards. Let's take a quick look to make sure we're familiar with them before proceeding. Next, we cover the key concepts that support machine safety. These concepts include risk assessment, hazard identification, and the implementation of protective measures. By understanding these core ideas, we'll be better equipped to apply the principles of ISO 12100 and other safety standards. In practical scenarios, we'll discuss most of these concepts in detail to ensure a solid understanding. The precise definitions of key terms are crucial for the effective understanding and implementation of safety standards. Here, we've selected some important definitions that we need to know. These definitions will clarify the language used in safety documentation and ensure that everyone is on the same page when discussing machine safety requirements and procedures. In the next slide, we cover more definitions. On this slide, we begin with the definition of safety function, one of the most important concepts in machine safety. A safety function is defined as a function of a machine whose failure can result in an immediate increase in risk. It's important to note that the definition of safety function in ISO 12100 is broad. It refers to any function performed by the machine itself, the control system, the operator, or through mechanical design that contributes to risk reduction. In other words, safety function in ISO 12100 is an umbrella term, not limited to control systems alone. This slide also highlights other key definitions related to protective measures, including inherently safe design measures, safeguarding, and information for use. Although we won't cover all definitions here, you can find them in ISO 12100. Let's look at a simple example: safety functions in a car. What are the typical safety functions? Take a moment to think about it. The most obvious answers are the airbag and the seat belt. But what about the steering or the gas pedal? Based on the definition of a safety function, a function of a machine whose failure can result in an immediate increase in risk, the steering system, the brake pedal, the gas pedal, the airbag, and the seat belt are all safety functions. But now, think about this for a moment. If you had to choose, would you drive a car without an airbag or a car without steering? The answer is clear. Steering is essential. This example shows that, even though all of these are called safety functions, they do not have the same level of importance. Some functions prevent hazardous situations from occurring in the first place. Others reduce the consequences only after a hazardous event has already started. Now, we introduce the approach to risk assessment and risk reduction procedures. We'll review these topics in this part, while we'll discuss risk assessment in Part 2 and risk reduction in Part 3 in detail. We begin with risk assessment, involving a systematic series of logical steps for analyzing and evaluating machine risks. As the diagram shows, risk assessment involves both risk analysis and risk evaluation. Risk analysis comprises the steps of establishing the machinery's limits, identifying potential hazards and risky situations, and estimating the level of risk associated with each hazard. Risk evaluation then determines the overall risk and the need for safety improvements. This systematic approach ensures a thorough analysis and evaluation of machine risks. Join us as we walk through these essential steps together in the upcoming slides. After assessing risks, the next step is to apply protective measures to eliminate hazards or reduce risks. These measures involve both designers and users. As shown in the diagram, design stage measures are prioritized since they are usually more effective than those added later by the user. ISO 12100 describes this hierarchy of measures in the three-step method. Step 1, inherently safe design measures. Step 2, safeguarding and complementary protective measures. Step 3, information for use. We emphasize that Step 1, implementing inherently safe design measures, holds significant importance among the 3 steps outlined. Subsequently, Step 2 takes priority over Step 3. In some cases, it may be necessary to repeat this process to further eliminate hazards and enhance safety through additional protective measures. Our goal is to minimize risks as much as practicable, while ensuring machine safety throughout its life cycle, maintaining usability, and balancing costs for manufacturing, operation, and dismantling. Now, let's get familiar with the main types of machine hazards. They include mechanical, electrical, thermal, noise, vibration, radiation, material, ergonomic, and environmental hazards. Each hazard has a source and potential consequences. Sometimes it's enough to focus on either the source or the consequence of a hazard, especially when several hazards occur in the same zone and share protective measures. The choice depends on which approach is more helpful for selecting effective risk reduction measures. In many cases, hazards that occur within the same hazard zone can be addressed by a single safety function, as long as that function effectively reduces the risks for all of them. This is why identifying hazard zones and understanding how hazards relate to each other is so important. In the next slides, we'll look at practical examples of these hazards. Let's begin with examples of mechanical hazards. First example, cutting or severing, resulting from cutting parts. Second example, crushing or impact, resulting from moving elements. Third example, severing or entanglement, resulting from rotating or moving elements. Fourth example, crushing or trapping, resulting from gravity or instability. Fifth example, crushing or impact, resulting from falling objects. Here are examples of electrical, vibration, and noise hazards. First example, electric shock or burn, resulting from live electrical parts. Second example, osteoarticular disorder or vascular disorder, resulting from vibrating equipment. Third example, fatigue or hearing impairment, resulting from noisy manufacturing processes. Examples of other hazards, including radiation, material, or substance, and ergonomic hazards. First example, burn, or damage to eyes and skin due to laser beam. Second example, breathing difficulties or explosion due to dust. Third example, discomfort or fatigue due to ergonomic hazard. We finish this part with a common example of thermal hazards, especially in foundries and metal production. When molten metal comes into contact with the water instantly flashes into steam, expanding rapidly and causing molten metal to splash or even erupt. Even a very small amount of moisture on tools, ladles, troughs, molds, or anywhere in the surrounding work area can be enough to trigger a violent reaction. Proper drying of equipment, careful control of moisture, and strict housekeeping practices are essential to prevent this type of thermal hazard. Welcome to Part 2, Risk Assessment. In this section, we focus on the details of risk assessment. Risk assessment involves defining the machine's limits, identifying hazards, estimating risk, and deciding on effective measures. Let's start this journey with a fundamental understanding. As we mentioned earlier, the risk assessment process consists of two key components: risk analysis and risk evaluation. In risk analysis, we gather crucial information that forms the basis for risk evaluation. This includes the machine's limits, hazard identification, and risk estimation. This stage enables us to make well-informed decisions regarding the need for risk reduction. These decisions are reinforced by qualitative or quantitative risk estimates, providing insights into machine hazards. To carry out a thorough risk assessment, we rely on several key sources of information. First, the machine profile. This includes user specifications, predicted machine specifications, past design documentation of similar machinery, and available usage guidelines. Second, regulations, standards, and documents. These cover relevant regulations, standards, technical specifications, and safety data sheets. Third, practical experience. This involves any accident, incident, or malfunction history of the machinery, health issues from emissions and chemicals used, and user feedback on similar machines. And finally, ergonomic principles. This information requires regular updates during design development or when machine modifications occur. Now, we discuss the first step of the risk assessment process, the limits of the machinery. The limits of the machinery serve as the foundational point for risk assessment, covering various aspects throughout the machinery's life cycle. These include use limits, incorporating the intended use and reasonably foreseeable misuse, space limits, time limits, and other specified limits. We'll go through these limits in the next slide quickly. Use limits cover the full range of machine operation and user interaction. This involves user specifications such as age and dominant hand usage, required training or experience level, and potential exposure of others to hazards. Space or geometry limits require evaluation based on the movement range, the space needed for individuals interacting with the machine during operation and maintenance, the human-machine interface, and the machine power supply interface. Time, or life cycle limits, include the expected lifetime of the machine and its components, considering intended use and reasonably foreseeable misuse, along with recommended service intervals. Additional limits come into play, including process parameters, required cleanliness levels, and environmental factors like temperature, pressure, and weather. The next key step in risk assessment is identifying hazards and hazardous situations across the machine's entire life cycle. This includes transportation, assembly, installation, commissioning, use, and dismantling stages, every step of the way. To identify hazards, we must look at both the tasks performed by individuals interacting with the machinery and the operations carried out by the machine itself. Task identification includes all human-machine interactions, such as setup, testing, programming, operation modes, maintenance, and cleaning. It's also important to recognize additional foreseeable hazards, which are not directly tied to tasks. Operation identification will be covered in the next slide. Operation identification has two parts: the machine's possible states and the unintended operator behavior, including foreseeable misuse. For machine states, we distinguish between, first, operating as intended, when the machine runs smoothly, performing its designed functions. Second, not operating as intended, or malfunctioning due to factors like material variations, component failures, or external disturbances such as shocks or electromagnetic interference. Equally important is unintended operator behavior or foreseeable misuse. For example, losing control, becoming distracted, or taking shortcuts. The next slide will show some examples. Here are some examples of unintended operator behavior or foreseeable misuse. First example, an operator uses a lathe machine while texting, causing an accident due to loss of focus. Second example, a worker continues using a malfunctioning conveyor, despite warning signs risking injury or breakdown. Third example, an employee tries to clean dirt off their skin and clothes using a high-pressure air compressor, leading to eye injuries and infections. Fourth example, workers use forklifts as makeshift platforms to reach high shelves or perform overhead tasks, creating risks of tip-overs, falls, and instability. After identifying hazards and hazardous situations, the next step is to estimate their risk by defining key parameters. Risk depends on two main elements. First, the severity of harm. This refers to the potential damage or injury caused by hazards. Second, the probability of occurrence of that harm. This describes how likely it is for the harm to happen, often expressed as frequency, such as the number of incidents per year. By combining severity and probability, we can determine the overall risk level for a specific scenario. Let's start with the severity of harm. which focuses on the potential consequences if something goes wrong. Severity can be estimated by considering the following factors. First, the severity of injuries or health damage. This ranges from minor injuries to serious harm or even fatal harm. Second, the extent of harm. This considers whether one person or several could be affected. In risk assessment, we usually evaluate the most likely severity, but we must also take into account the highest foreseeable severity, even if it is unlikely. Now, let's move to the probability of occurrence of harm. This is estimated by looking at three key aspects. First, exposure to the hazard. This considers how often and how long individuals are in the hazard zone, the method they access it, and how many people are involved. Second, occurrence of a hazardous event. This is the likelihood of the event happening based on reliability data, accident history, or health-related incidents. Third, possibility of avoiding or limiting harm. This looks at how quickly a hazardous situation could escalate into harm, whether individuals are aware of the risk and their ability or experience to avoid or reduce it. Together, these factors determine how likely it is that harm will happen. When designing machinery, compliance with safety regulations is essential. The new EU machinery regulation, which replaces the Machinery Directive, requires that machinery be designed and built in accordance with all applicable EU legislation, such as the Pressure Equipment Directive, PED, and the ATEX Directive for equipment used in explosive atmospheres, as well as relevant harmonized standards like IEC 62061 and others. By harmonized standards, we mean standards recognized by the European Committee for Standardization, CEN. Following these standards supports both regulatory compliance and safety by design. Let's look at how this works in practice, using a furnace equipped with a burner as an example. First, hazard identification. We start with ISO 12100, a Type A standard, to identify hazards in the system. Some hazards may be directly related to control system failures, or may require risk reduction through a safety function performed by a safety-related control system. For more complex systems, especially those involving process control, we recommend a hazard and operability study, HAZOOP, as a systematic method for identifying hazards and operational issues in integrated machinery. Second, determining the required risk reduction using IEC 62061. IEC 62061 applies the safety integrity level, SIL, concept to express the confidence that a safety function will perform as required. As a Type B standard, IEC 62061 is used to determine the required SIL for each safety function implemented by a safety-related control system. Unfortunately, IEC 62061 redefines the term safety function differently than from ISO 12100, limiting it only to functions implemented by safety-related control systems. This can create some confusion. In our course, we use the term Safety Instrumented Function, SIF, to clearly distinguish between the general safety function in ISO 12100 and the control system-specific safety function in IEC 62061. Finally, detailed risk analysis. ISO 13577 Part 2, a Type C standard, provides detailed requirements for combustion and burner-specific risks. Before we go further, let's take a moment to talk about SIL levels. There are 4 safety integrity levels in total, SIL 1 up to SIL 4, as shown in the figure. SIL 4 represents the highest level of safety integrity, and SIL 1 the lowest. However, in machinery standards such as IEC 62061, only SIL 1 to SIL 3 are used. SIL 4 is generally not required in machine safety context. In contrast, process industry standards, such as IEC 61511, do use SIL 4 for very high-risk applications. SIL levels can be expressed in 2 ways, PFH and PFD. PFH is the probability of dangerous failure per hour, and is used for high-demand or continuous safety instrumented functions, such as guard interlock monitoring. PFD is the probability of failure on demand and is used for low-demand functions, such as emergency stop activation, where a demand occurs less than once per year. The SIL level is the same in both cases, but the numerical range differs depending on whether PFH or PFD applies. To make the PFH values easier to remember, we can roughly convert them from per hour to per year by using the approximation that 1 year is about 10,000 hours. And since PFD is already based on demands, the same power of 10 pattern applies. With this simplification, here's an easy way to remember SIL levels for both PFH and PFD. SIL 1 corresponds to 1 dangerous failure per 10 to the power of 1. SIL 2 corresponds to 1 per 10 to the power of 2. SIL 3 corresponds to 1 per 10 to the power of 3. And SIL 4, used mainly in the process industry, corresponds to 1 per 10 to the power of 4. Now, let's move forward and see how these safety integrity levels are selected during the risk estimation process. Let's continue with risk estimation by introducing safety integrity level, or SIL assignment, like ISO 12100. IEC 62061 defines risk parameters, the severity of harm, and the probability of its occurrence. Severity of harm is rated from 1 to 4. 4. Fatal or very severe, irreversible injury, cannot return to the same work. 3. Major or irreversible injury may still allow work after healing, for example, a broken limb. 2. Reversible injury, needing medical treatment, for example, deep cuts. 1. Minor injury, needing only first aid, for example, scratches. Probability of harm occurrence is based on 3 parameters. First, frequency and duration of exposure, FR. This is how often and how long a person is in the hazard zone, for example, during material feeding or adjustments. Second, probability of a hazardous event, PR. This is the likelihood of an event due to machine behavior or human error, for example, stress, lack of training, or complexity. Third, possibility of avoiding or limiting harm, AVI. This considers how easily a person can avoid or reduce harm, depending on the speed of the hazard, ability to retreat, visibility of danger, and machine characteristics, for example, sharp, hot, or electrical. The appropriate value should be selected for each of these 3 parameters to assign the correct SIL. The class of probability of harm, CL, is defined as the sum of 3 parameters: frequency and duration of exposure, FR, probability of a hazardous event, PR, and possibility of avoiding or limiting harm, AV. For SIL assignment, we use the table shown on this slide. The SIL requirement is determined at the point where the severity, SE, row intersects with the corresponding CL column. The orange areas indicate the SIL levels required for a safety instrumented function, SIF, while the light green areas indicate that other measures, OM, should be considered instead of assigning a SIL. Example of SIL assignment for a SIF. Consider a metal stamping machine in a manufacturing facility with a risk of crush injuries. Severity, SE, is 4. Fatal or serious injuries, including potential loss of limb. Frequency, FR, is 4. Frequent or continuous exposure to the hazard. The operator is regularly in the danger zone during normal operation. Probability, PR, is 3. Possible under normal conditions. Hazardous events may occur, but not with the highest likelihood. Avoidance, AV, is 3. Limited ability to avoid harm due to machine layout or short reaction time. This gives a class of probability, CL, equal to 10. According to IEC 62061, with SE equal to 4 and CL equal to 10, the required SIL is SIL 2. This SIL applies to the safety-related control function designed to mitigate the stamping hazard. This table shows an example of risk assessment documentation and SIL assignment from IEC 62061. This table illustrates how ISO 13577 Part 2, a Type C standard, applies IEC 62061, a Type B standard, to determine SIL requirements for identified hazards. ISO 13577 Part 2 focuses on combustion and fuel handling systems. The excerpt you see here comes from Table D1, which provides typical values for industrial furnaces and related processing equipment. Here, there are two examples of SIL 3 requirements. ISO 13577 Part 2 uses the term SRCF, meaning Safety-Related Control Function. As mentioned earlier, in this course, we use the term SIF for the same concept. Now let's move on to risk evaluation. Risk evaluation follows risk estimation to decide if further measures are needed. Using the three-step method, risks are reduced to the lowest practicable level while keeping safeguards compatible and maintaining usability. Risks can be compared with similar machinery, but this never replaces a full machine-specific risk assessment. For example, risks from a bandsaw used for cutting meat differ greatly from those for cutting wood. In the next section, the three-step method for risk reduction will be discussed. Welcome to Part 3, Risk Reduction. In this section, we complete our overview of ISO 12100 by focusing on how risks are reduced. Risk reduction is achieved through inherently safe design measures, safeguarding, and complementary protective measures, and clear information for use. We'll look at each of these in detail. Let's begin with the fundamentals. The goal of risk reduction is to either eliminate hazards or reduce both the severity and likelihood of harm. This is achieved through the application of protective measures in a specific sequence, known as the three-step method. First, inherently safe design measures. This step involves designing the machinery in a way that inherently minimizes risks, emphasizing safety at the core of the design. Second, safeguarding and/or complementary protective measures. This step introduces safeguards and complementary protective measures to further mitigate risks during machine operation. Third, information for use. This step involves providing comprehensive information for use, ensuring that operators are well informed about potential risks and proper usage. We'll now look at each step in more detail. Let's start with the first step of risk reduction, inherently safe design measures. This step is the most important because safety features built directly into the machine are generally more reliable and effective over time. Experience shows that safeguards can fail or be bypassed, and instructions may not always be followed consistently. Inherently safe design measures are achieved through design choices made during the machine's development, either in the machine itself or in how individuals interact with it. The aim is to eliminate hazards where possible or reduce risks by designing features that minimize potential dangers at the source. Now, let's connect this back to the initial definition of safety function and the car example we had in Part 1. In a car, the steering, the gas pedal, and the brake pedal belong to Step 1. Inherently safe design. They directly influence how the machine behaves, and they help avoid dangerous situations before they occur. Then we have the seatbelt and the airbag. These fall under Step 2, safeguarding. They do not prevent the hazard. Instead, they reduce the harm if an accident happens. This example shows exactly why inherently safe design is always priority number 1, because preventing a hazard is always more effective than trying to protect against it afterward. As shown in the diagram, when applying inherently safe design measures, several factors are considered. These include geometrical aspects, physical characteristics, general technical design knowledge, inherently safe measures for automation and control systems, and more. By definition, Automation and control systems designed for inherent safety are part of inherently safe design. In the following slides, we'll explore practical examples of these factors. Let's look at some examples of geometrical factors and physical aspects in inherently safe design. Geometrical factors. First example, visibility and control. A construction crane should allow maximum direct visibility of working areas and hazard zones. Second example, avoiding hazards. In a vegetable slicing machine, sharp edges, corners, protruding parts, and unnecessary openings should be eliminated. Physical aspects. First example, limiting actuating force. Collaborative robots, or cobots, are designed so that if they hit or squeeze a person, the limited force prevents harm. Second example, reducing kinetic energy. Conveyor systems can be designed with restricted mass and velocity to reduce kinetic energy and improve safety. Next, we'll review further factors related to inherently safe design measures. In this slide, we highlight two other key factors for inherently safe machine design. Positive mechanical action. First example, to operate a press brake. A foot pedal with direct mechanical linkage, requiring full depression. Second example, a two-button system that must be pressed simultaneously to activate the machine. Stability provisions. First example, a tall drilling machine bolted to the floor to prevent tipping during operation. Second example, a mobile scissor lift with outriggers to widen its base and ensure stability for preventing tipping. Let's now look at an important topic, applying inherently safe design measures to control systems. The control system must be designed so that its safety-related performance provides a sufficient level of risk reduction as defined in ISO 13849 Part 1 or IEC 62061. In essence, the control system enables the operator to interact with the machine safely and efficiently. Achieving this may involve one or several of the solutions shown on this slide. Control systems should also limit the movement of machine parts, the machine itself, or any loads it handles, keeping them within safe design parameters such as range, speed, acceleration, and load capacity. Dynamic effects, like load swinging, must also be considered. In the following slides, we'll take a closer look at how inherently safe design measures can be applied to control systems. This diagram highlights key concepts in designing a safe control system. Each concept plays an important role in ensuring the machine operates safely and reliably. In the next slide, we'll explore examples of two of these concepts for a closer look at their importance. Here are some examples of inherently safe design measures in control systems. Starting and stopping mechanisms. For example, a car engine starts only when it's in park mode and the brake pedal is pressed. Automatic monitoring. For example, a pneumatic press shuts down automatically if pressure drops below safe levels, preventing uncontrolled motion. As a final point on inherently safe design measures, let's look at mechanization and automation. Mechanization still involves the operator, but it removes the most hazardous manual steps. A good example, a centralized lubrication system. Instead of workers applying grease close to moving parts, the system distributes lubrication from a central pump. This reduces exposure to hazards, while the operator still handles monitoring and refilling. Automation, on the other hand, requires little or no operator involvement. The system performs tasks independently. For example, an automatic conveyor can remove a metal part from the machine and transport it without any operator handling. Now let's move on to the second step of the risk reduction process, safeguarding and complementary protective measures. When inherently safe design cannot fully eliminate hazards or reduce risks, we use guards and protective devices to protect individuals. ISO 12100 outlines this step in 4 key areas: selection and implementation, choosing and applying the right guards and protective devices to minimize risks. Design requirements, ensuring guards and devices meet safety standards and criteria. Safeguarding to reduce emissions, addressing not only physical hazards, but also emissions such as noise, vibration, hazardous substances, and radiation. And finally, complementary protective measures, adding equipment like emergency stop devices to further enhance safety. In the next slides, we'll explore details and examples to see how these measures play a vital role in risk reduction. Now let's focus on how we choose and implement guards and protective devices. This step is crucial in safeguarding individuals against potential hazards from moving parts. We consider both the nature of these parts and the need for access to danger zones. Here are key considerations in this process. Safeguards are selected based on the machine's risk assessment. If the required risk reduction is not achieved by inherent safe measures, safeguarding is the next step. Fixed guards are suitable when no operator access is needed during normal operation. For frequent access, once per week or more, movable interlocking guards, or sensitive protective equipment, are required. In some cases, a combination of different safeguards provides complete protection. We design enclosures for control positions and intervention zones to provide protection against multiple hazards, including falling or ejected objects. Enclosures should guard against them with FOPs, falling object protection structures. Emission hazards. Enclosures help reduce noise, vibration, radiation, and exposure to harmful substances, ensuring a safer environment. Environmental factors. Well-designed enclosures mitigate risks from extreme temperatures and adverse weather. Machinery tipping or rollover. Incorporating rollover or tip-over protection structures, ROPS, TOPS, helps prevent accidents caused by unstable machinery. Here are examples of enclosures for control positions and intervention zones, protecting operators from multiple hazards at once. First example, falling or ejected objects. A mining excavator cab with a heavy-duty steel roof grid shields the operator from falling rocks, while the operator sits safely inside. Second example, emissions. A CNC machine fully enclosed with transparent panels contains dust and noise, allowing safe observation without hearing protection. Third example, environmental hazards. A tower crane cab with heating and cooling vents protects the operator from snow, sun, and extreme temperatures. Fourth example, machine instability. A tractor tipping on a slope where the driver remains protected inside a rollover protection structure frame. When selecting and implementing guards and protective devices, different scenarios must be considered to ensure comprehensive safety. Each scenario offers several options. These scenarios can be where access to the hazard zone is not required during normal operation, or where access to the hazard zone is required during normal operation, or where access to the hazard zone is required for machine setting, teaching, process changeover, fault finding, cleaning, or maintenance. Here are examples of safeguards and protective equipment. Fixed guards, a conveyor drive unit with a metal mesh cover bolted in place over the gears and chain. A worker is nearby, but hands cannot reach the moving parts. Interlocking guards, with or without guard locking. For example, a lathe with a safety door. When the door is opened, the chuck stops rotating instantly. Self-closing guards, a circular saw with a spring-loaded cover. The cover slides back during cutting, then snaps back to cover the blade once the cut is done. Here are more examples of safeguards and protective equipment. Sensitive protective equipment. A press brake with a light curtain. The machine stops immediately if a hand breaks the beam. Two hand control devices. A punch press requires both buttons to be pressed simultaneously, keeping hands away from the hazard zone. Interlocking guard with start function, also called a control guard. For example, a robotic welding cell with a sliding gate. The cycle starts only after the gate is fully closed and locked. This diagram highlights the key points from ISO 12100 on the design requirements for guards and protective devices. These include general requirements, specific requirements for guards, technical characteristics of protective devices, and provisions for alternative types of safeguards. In this slide, we review the general requirements for designing guards and protective devices. They must be fit for their intended use, considering mechanical and other hazards, and be compatible with the machine's working environment. They should also resist defeat, minimize interference with machine operation, and discourage bypassing. Key requirements include strongly built, no introduction of new hazards, difficult to bypass or disable, adequate distance from danger zones, unobstructed view of the process, allowing essential tasks without full removal or disabling with access limited to the necessary area. Safeguarding to reduce emissions. If inherently safe design measures cannot sufficiently reduce emissions at the source, additional protective measures shall be applied. For example, for noise, this could include enclosures, machine-mounted screens, or silencers. This diagram shows examples of safeguards for noise, vibration, hazardous substances, and radiation. In addition to inherently safe design measures, safeguards, and information for use, we may need complementary protective measures based on the intended use and reasonably foreseeable misuse of the machine. Examples include emergency stop components and functions, escape and rescue provisions for trapped persons, isolation and energy dissipation measures, safe handling of machines and heavy components, and safe access provisions to machinery. Let's look at a few examples of complementary protective equipment. Emergency stop functions must be clearly identifiable, visible, and accessible. They should stop hazardous processes quickly without creating new risks and remain active until they're reset at the starting point, preventing any automatic restart. Escape and rescue. Examples include escape routes, shelters, movable elements, anchorage points for descender devices, and communication systems so trapped operators can call for help. Isolation and de-energizing, also known as lockout-tagout or LOTO. This procedure prevents the accidental release of hazardous energy during maintenance, repair, or cleaning. The equipment is shut down, isolated, locked, and tagged until authorized personnel complete the work and remove the devices. Now let's move on to the third step of the risk reduction process, information for use. Clear and complete instructions are essential to ensure machines are used safely by both professional and non-professional users. This guidance supports safe and proper operation in all situations. As shown in the diagram, ISO 12100 addresses this step in 5 key areas. 1. General requirements. 2. Location and nature of information. 3. Signals and warning devices. 4. Markings, signs, and written warnings. And 5. Accompanying documents, particularly the instruction handbook. Information for use is essential for safe operation, though its impact on risk reduction is often harder to quantify. Designers may find it difficult to justify risk reduction based solely on Step 3. General requirements include drafting clear machine information using text, symbols, and diagrams. This should cover intended use, operating modes, safety guidelines, such as training, protective equipment, and additional guards, acknowledgement of residual risks, expected uses, and warnings against foreseeable misuse. Here are some examples of the location and nature of information for use. On machine labeling, a hazard symbol placed near the rotating spindle of a milling machine, reminding the operator to stay alert while working. Instruction handbook, a user manual provided with the machine, containing clear and complete instructions for safe operation. Packaging information, safety symbols, and handling instructions displayed on the packaging to ensure safe transport and unpacking before use. Here are some examples of signals and warning devices. Flashing beacon before machine starts. A packaging machine with a yellow beacon that lights up a few seconds before the conveyor begins to move. Siren before robot movement. A robotic welding cell with a red siren that sounds just before the robot arm starts moving, warning nearby workers to stay clear. Overspeed warning light. An industrial centrifuge with a red overspeed light flashing on its control panel. The operator sees it and reaches for the stop button immediately. Comment by TroCo. From a professional technical safety engineer's point of view, signals and warning devices are strong indicators that this business has failed in achieving inherent safety. On the other hand, they may have a huge potential for improvement. Here are some examples of markings, signs, and written warnings. Maximum load marking on a crane. A clear label indicating the highest safe lifting capacity, helping operators avoid overloading. PPE requirement pictogram on a grinder. A safety sign reminding workers to wear protective equipment, such as goggles and gloves, before use. Pictograms for machine safety. Standardized symbols placed directly on equipment, ensuring quick and universal understanding of safety information. With these examples, we conclude this section on information for use. In the next slide, we'll finally sum up our course on machine safety. Let's wrap up with a quick summary. In this course, we covered key aspects of ISO 12100, focusing on machine safety, risk assessment, and risk reduction. We examined machine limits, hazard identification, and risk evaluation. Inherently safe design, safeguarding, and complementary protective measures were highlighted as essential for maintaining safety throughout the machine's life cycle. We also emphasized the importance of clear communication through information for use, warning signals, and documentation. By following ISO 12100 and its three-step risk reduction process, we can support safer design, operation, and maintenance of machinery, helping protect both people and productivity. We would like to highlight that a new edition of ISO 12100 is under development, with publication expected by mid or late 26. This revision includes key updates, such as alignment with machinery regulation, and new design aspects for cybersecurity, artificial intelligence, and hygiene. We will update this course as soon as the new edition is released, ensuring our training remains aligned with the latest machine safety standards. At Trondheim Consulting, TroCo, we thank you for joining us on this journey through machine safety, where safety is prioritized at every step. Our team brings practical engineering experience from industry, combining standards knowledge with real-world applications to support organizations throughout the design, risk assessment, risk reduction, and safe operation of machinery. For any inquiries, feel free to contact us by email or phone. Visit our website at troco.no for more details, and stay connected with us on LinkedIn and YouTube for updates. We look forward to supporting you in your machine safety work. Thank you once again for being part of our commitment to safety and professionalism.